Ideal gas law is an equation we use for this concept called an ideal gas, which I'll go over in a few slides. And essentially, it's an equation we use for these gases. So in our constant equation sheet on the back side, we have the equation that I highlighted in red on the top. Pervnert is what I pronounce it as. And so you could see what each of the letters stands for on the right side, because again, we're dealing with gases. So gas particles have a pressure because they're pushing on whatever container that they're in. And then obviously they take up space. So you got the volume and then temperature, moles, and so on. And there is a constant called R, and you can see that down there. So you could see that there's different R constants depending on what units you have. So make sure that you pay attention to the units when using Pervnert, because you might need to convert different things. So be very, very, very mindful of that. We also have the other equation that I have pointed out in orange, and that is based on absorbing gases and stuff, and we'll talk about that later. Now, one thing I do want to point out is the one in green, and that answer, 22.4 liters per mole, is a very, very, very common incorrect answer on MCQs. It's only an ideal gas at STP, and STP corresponds to standard temperature and pressure, and you could see the definition below, where STP is at 273.15 Kelvin and 1 atmosphere. So that is the standard, and it's only for those situations. So if you have an ideal gas not at the standard STP, then you would need to not use that relationship 22.4 liters per mole. So if you happen to know something about the gas being at STP, you probably won't need to use Pervnert. You would probably be able to just use the 22.4 liters per mole, and then you could do regular stoic with units canceling. So there are units that we need to deal with, as I mentioned previously, and so pressure has multiple units. So pressure has all of these conversions, so if pressure is given in atmospheres, you should be able to convert it to millimeters mercury, to torr, and to kPa. So the first three are on the constant equation sheet, but kPa is not. So you want to make sure that you remember that for converting purposes. So again, if you have an ideal gas law and you need to convert the units of pressure, make sure you're able to with units canceling and all that stuff. Again, know your units, convert, make sure that you can correspond these units are for pressure. If you are curious, millimeters mercury is based off an old way of measuring gases using literal mercury in a tube, and you see how much it increases in millimeters in that tube, and so that's why that is used as one of the measurements. But we usually don't focus on that one anymore. We usually focus on torr, which is why you could see that they mean the same thing, so just keep that in mind. Volume is going to be converted to liters. So if you look right here, you could see that the gas constants, the second and the third one, have it in liters. So if you're given milliliters or you're given some other unit for volume, make sure to convert it, because again, look at your gas constants. It is liters, so make sure that you do that. Temperature is related to mass and velocity because you have the speed at which the particles are moving and then how much mass they take, and you want to make sure that you convert it. It is on the constant equation sheet, so if you're given degrees Celsius, you just convert it to Kelvin and you're good. Okay, so you can see the R gas constant. As a reminder, if you have a -1 there, that means you have those units on the bottom. So if I'm looking at the first one, we have joules and then moles -1 and K -1. So that means the moles and the K would be in the denominator. Again, notice that they're all K. So again, make sure that you can convert any of the temperatures to degrees Celsius. STP, as I mentioned earlier, is the standard temperature and pressure. So if you have a problem and it mentions the temperature and pressure and it happens to match STP, then you can use the ideal gas that I have mentioned with the 22.4 liters per mole. With PervNERT, we have ideal gases. And so let's go over what an ideal gas is. So an ideal gas is a theoretical concept. It is not real at all because nature is a lot more complicated. However, the calculations that we use with ideal gases, like PervNERT and other stuff, is really, really close to how it can be with real gases. And so a lot of the time it's a very good estimate, which is why we use it. But we still need to define what an ideal gas is. So an ideal gas, we say, have no IMFs. Gases still have IMFs. They interact when they're near each other. So there's some kind of interaction when they're molecules. So just keep that in mind. They have negligible volume, meaning we pretend that they're like a dot. We pretend they're a point and they don't take up space. Now, gases, depending on what type of gas they are, will take up actual space. So you know that molecules have a certain amount of radii for their atoms, and so the molecules will be a certain amount of space they take. But for ideal gases, we pretend that they're just a dot. They don't take up any space that is important for this definition. And we also assume they have random movement. Now, gases we usually think about kind of zoom in past each other kind of randomly, but again, with IMFs or with other kinds of things happening, with attractions, they're not going to always be random. You can have gases that might be attracted to certain parts of a thing or parts of a mixture or whatever. And so that's why in an ideal gas, we say it is completely random. We also say, along with the volume being a dot, that they're all equally sized. So if I have an ideal gas of one compound and an ideal gas of another, even if they have drastically different sizes in real life, we pretend they're equal for the sake of using it as an ideal gas. So the gas law is PervNERT. So you use PervNERT in order to calculate a certain variable, whatever variable you need. And so you want to be mindful of the units. And so I have some practice problems here. And one thing that's handy is using the guess method. So what are your givens? What are your unknowns? What's your equation you use? How do you manipulate it? And subbing and solving. So go ahead and try this out. All right, ready? Here we go. So for the first problem, I'm going to do the guess method and organize my information. So first I have my givens. Now, I noticed that mass was given, but PervNERT has moles. So I converted the grams to moles using the molar mass of CO2. And then the other givens I have, well, it told me it's STP. And so at STP, I have a temperature and pressure definition from our constant equation sheet. So I listed that here as well. And then I have an R value, and remember, there are 3 different versions of R, so I want to make sure I use the one where the units match, which is what I have down there. And then obviously the unknown is V because it says determine the volume. And so I'm going to go ahead and take the equation PervNERT. I'm going to solve for V since it's the unknown, and so then I have my equation right over here. I take that equation, I substitute the values that we have, and then I cancel out units and I get liters in the end, and then that makes sense because volume is liters, and so I get my liters. I round to 3 sig figs because of the sig figs involved. I have highlighted here where the sig figs came from, and then I just kept extra units because I like to round at the very end when I am actually doing sig figs. So there we go. Okay, now for number 2. So we're trying to get the molecular weight of this gas, and so the molecular weight corresponds to molar mass. And so again, I can list my givens. So I have my mass, my volume, again it's STP, so I have my pressure and my temperature. Now, because I know this is STP, if I looked at the volume here, it's 22.4 liters. And if you look at your constant equation sheet, if you have a gas at STP, 1 mole takes up 22.4 liters of space. And so because that is the case, I could literally just take the grams that was given in the problem, and so then I could just get the molar mass by literally dividing by 1 mole, and then that's the molar mass. Now, if you wanted to, you could do the whole calculation with Pervenert, and you would have gotten the amount of moles, which ends up being approximately 1, and then you would get the molecular weight by doing mass divided by moles. Again, because of this shortcut with STP, I was able to already just notice that pattern. But if you didn't notice the pattern, it doesn't hurt to go through Pervenert, and you would have gotten the answer anyway. So if you just blank out and don't know if it follows STP patterns, then just do the math with the equation, and you're totally fine. Okay, so third one. So we're getting the molecular weight of something. And so I list my givens because I like to list my givens. Notice that I have converted my temperature to Kelvin because remember that gas constant is in Kelvin. And so based off the units that were given in this problem, I need to convert. So I decided to convert the R value into millimeters of mercury. However, I could have converted the pressure into one of the other pressure units, and then I could have used a different R value. All of these methods end up being the same kind of thing, so you just want to keep that in mind. You can convert any units you feel like. And so my unknown, well, first I need to get my N, and then in order to get the molecular weight, I need the molar mass. So I use the N value and I use the grams that were given in the mass in order to calculate the actual molar mass. And so I continue calculating this problem. I use Pervenert and then solve for N. I showed my units canceling here just to show the point that I end up getting moles at the end, because I have it in the denominator of a denominator, so I can brush that out into the numerator, which is why it's moles. And then I highlighted where the lowest amount of sig figs are, which was 3. And so molecular weight, I take the grams, I divide by the moles, and then I get my molar mass, as we got here. Because Pervenert and ideal gases are all variables, right? P can relate to V, can relate to T, could relate to N. We can have different relationships and talk about how they're direct or inverse. And so using Pervenert, we can figure that out. And so we're comparing gases at different scenarios. So if I have, for example, the same temperature and the same amount of moles, I can see if I increase pressure, what happens to volume. And again, you could just compare any variables you like. You should be able to, as I said here, interpret relationships from graphs. And so we're going to actually interpret some graphs right now. So here is a general axis. And so we have something called Boyle's law. You don't need to know that it's called Boyle's law, but we're looking at the relationship between P and V, so pressure and volume. And so we have an inverse relationship with this because if I just look at the equation, if I plugged in some random values and increased one of them, then the other one is going to decrease. So how do we graph this? Well, I can show that with rudimentary axes. So we're not going to put actual values to this, but you should be able to draw these relationships if they give you a random one. Now, again, you don't have to necessarily remember this, and I'll explain why in a second, because it's easy to remember with the combined gas law, which again, we'll talk about in a second. And so on this graph, I could put, for example, pressure over here. And then I could put my volume down here. And so because this is an inverse relationship, if I increase P, then V decreases. If I decrease P, then V increases. And so my graph will look something like this, where again, as I increase P, V is decreasing, right? And then if I decrease P, V is increasing. So it's an inverse relationship. So you just want to make sure that you could draw that. and show how pressure and volume are related. So we could do the same thing for other relationships. So we have Avogadro's law, and so we're relating volume with moles. And so this is a direct relationship. And so a direct one means if I increase one variable, then I'm increasing the other variable. So in my graph here, I can have on the y-axis the volume, and then on the x-axis, I can have my number of moles. And since it's a direct relationship, as I increase volume, I increase moles, it's going to go in this general direction here. So Charles' law is the other law that we do, and it is a direct relationship similarly to the other one. So if I increase V, I increase T. And so when I'm showing this on the graph, I could, for example, put volume over here. I could put temperature over here. And so it's going to be a straight line going up because, again, as volume increases, temperature increases. If volume decreases, temperature decreases. And then the last one is Guy-Lussac. And so we're relating pressure to temperature. And so this is also a direct relationship. So if I have pressure over on the y-axis and I have temperature on the x-axis, then I'm going to have a straight line because, again, direct relationship. As pressure increases, volume increases. And so all of these relationships you can memorize if you want to. You don't need to know the names. Personally, I just look at the combined gas law, which is PV divided by T is equal to PV divided by T. The 1s and the 2s correspond to the different scenarios that you have. As I said earlier, all the laws that I mentioned previously with the graphs are in this equation, right? So if I look at Boyle's law, it's PV and PV. Well, temperature is constant in that case, and moles would be constant in that case. And so I don't memorize the different relationships personally. I just know the combined gas law and then remove the variable that is, constant. And so that's pretty much how I personally remember it. And then I see which one's increasing versus which one's decreasing. So units for this combined gas law equation. So combined gas law equation is not on your constant equation sheet. So make sure that you know this equation. But for this particular equation, you cannot use degrees Celsius ever. This makes sense because on the bottom, you have temperature. If your degrees Celsius ends up measuring to 0, well, I can't divide by 0. So you want to make sure that you convert to Kelvin because scale-wise that makes sense. So make sure just to have your temperature be in Kelvin. Okay, here is an example problem where we use that combined gas law. And so I read this problem, I find out what the variables are, and then I plug and chug. So we have a volume. So we have an initial volume, so that's going to be our V1. If you want to write VI instead of V1 for initial, that's fine too. It's whatever you feel like doing. And so I'm going to label that as 4 liters. I have an initial temperature and a final temperature. So my T1 is going to be 10 degrees Celsius, and my T2 is going to be 20 degrees Celsius. And as I said earlier, you want to make sure you convert these to Kelvin. So I'm going to go ahead and get this to 283 Kelvin. And then this is going to be 293 Kelvin. And so I keep, reading the problem and I see what information I have here. I notice it says, what will the volume of the gas be? So that's going to be my unknown. So V2 is my unknown. It also says the pressure is held constant. Since it's held constant, that means P1 equals P2. So I'm going to go ahead and take the combined gas law. So P1 V1 divided by T1 equals the same thing but with the different scenario. And so since my pressures are constant, I'm going to go ahead and get rid of them because they cancel out. And then I'm going to go ahead and multiply both sides by T2. So I end up getting V1 T2 divided by T1 equals V2. Because again, V2 is what we're solving for over here. And so I'm going to go ahead and just plug and chug. So my V is going to be 4 liters, as I have here. And then my second temperature was 293 Kelvin. And then my first temperature is 283 Kelvin. So again, that's going to be my V2. And so when I plug and chug, I get 4.14 liters. Now, I put this as 3 sig figs because all of the original values given in the problem were 3. As a reminder, temperature conversion is a definition, so that wouldn't count in sig figs, so keep that in mind. Cool. Okay, so we have this your turn. So I recommend organizing your givens based off P1, V1, T1, and then knowing again which one's the initial versus what's the after. So go ahead and pause this video and try these problems yourself. All right, ready? Here we go. Okay. So I organized my information on the left. I put all the information there. I made sure to convert all my temperatures into Kelvin, and I'm solving for V2. I took the original combined gas law and then I reorganized it, so I'm solving for V2. That means I multiplied both sides by T2 and I divided both sides by P2. And then I just plug in my values based off the givens and I get my answer. Notice it's 3 sig figs because I have 4 sig figs on the volume, but my degrees Celsius was given in 3 sig figs, my pressure was given in 4, I have the least amount because this is all multiplying as 3, and notice I put a period because if I only put 100, that's 1 sig fig. If I put 100 point, that means that those zeros actually matter. So just keep that in mind for calculation purposes. In the second one, I did the same thing. I reorganized my information. It says the gas is at 25 degrees Celsius. Now, it doesn't mention a second temperature, so the assumption is it's constant, which is why I have T1 equals T2 as written on the screen. So just keep that in mind. Again, I just took the combined gas law, I did some multiplying and dividing in order to get where I needed to go. I canceled out the temperatures because again, they're constant. So then I just plug and chug and then I get 3 sig figs at the end. Now, we can practice an FRQ-like problem with this information. So here is 3 different graphs. And so you look at the graphs and you notice some information. So pretty much what this FRQ would be like is it wants you to describe what is happening in each graph and what kind of relationship is here. And so you want to go ahead and talk about what's happening, like as something increases, what is happening to the other variable, and then what kind of relationship is it. So go ahead and pause the video and try it out. All right, ready? Here we go. So we talk about each graph. The first graph, you see volume decreasing, pressure increases, and we can also state the vice versa of that. And that's an inverse relationship. Second graph, we have the temperature increasing, the volume's increasing. We can also say as temperature decreases, volume decreases, and so therefore that's a direct relationship. And then the same thing with pressure and temperature. As temperature increases, pressure increases, and if temperature is decreasing, pressure is decreasing, and that's direct. So make sure that even if it's not these particular relationships, that you can look at a graph and know, hey, that for sure is inverse or direct, and then describe what exactly is happening on that graph. So other things we do is mixtures of ideal gases. So I can have an ideal gas of one compound, an ideal gas of another, and so I can mix them together and talk about what that is. And so we have a mixture. We can define them by each component. So we have, for example, 2 gases. both of the gases apply pressure in some way. So since gas 1 applies one pressure, gas 2 applies another pressure, we can call these partial pressures because they're in a mixture. Because again, one gas does one thing, another gas does another thing. It is independent of the other components because remember, these are ideal gases. If they were not ideal, then the different gases in a mixture would affect each other because again, IMFs and other things that can happen. So again, this is for ideal gases. We pretend they're ideal, therefore they would be independent of each other. So we have Dalton's law of partial pressures, which is the thing that I was just describing. And so we have some equations for that. And so here we have the other equations that are on our constant equation sheet. And so you have here the PA, P total, this X. What the heck is all this, right? So let's actually talk about the third equation first. So this third equation here is the total pressure. If this gas was made out of 3 different gases, you have PA, PB, PC. Those are the different gases that we would correspond to. Now, if I knew one of these variables, then I could potentially solve for another variable. Again, it depends on how many things I have. So if I am talking about one individual gas, so let's say I'm talking about A, that is one of the gases, I can take the partial pressure of that gas and I could solve information about it by using the second equation. So you see I have my total pressure, I have my partial pressure of gas A, and then I have this XA, which corresponds to the moles of whatever substance A is, to the total amount of moles in the mixture. So if I had like 20 moles in the mixture and A corresponded to 5, then 5 divided by 20, and then you could plug into this to solve for any variable. So just being able to manipulate these equations in order to do that. So again, a mixture of ideal gases is literally just gases mixed together that are ideal, so they're independent of each other, and so there could be any number of them. Okay, I have 3 practice problems relating to the partial gas equations that are listed earlier. So go ahead and pause the video and try doing these yourself before I talk about it. All right, ready? Here we go. Okay, so for the first one, I have the sample A gas, and it evaporates over water. It's a closed system, meaning nothing can escape, no gases can escape. And so if I know the total pressure and I know how much the water vapor, aka the gaseous water, has a pressure of 1, then I can go ahead and subtract the total from the amount from water in order to get the pressure of gas A. Notice that torr and ATM are given, so you want to make sure you convert one to the other. It does not matter which one you convert to, so I decided to convert the 780 torr to be atmospheres instead. So I changed the total pressure to be 1.03 atmospheres, and then I got my torr. I go ahead and subtract in order to get my PA. And so my PA is just the total minus the, again, water gas, which was 1, and then I get 0.03. So the gas A has a pressure of 0.03 atmospheres. Cool. For the second one, this one's really easy. It's just asking for the total number of moles in the system, aka you have a bunch of gases and it's in a closed container. Now notice both problems talked about closed containers or closed systems. If it was open, that means you're exposed to the other gases in the air. Just in the surrounding environment, whatever gases happen to be there. But because this is in a closed container, no gas can enter or escape. And so that means I could literally just add them all up in order to get the number of moles. So I literally just did that on the bottom, which I got 30 moles at the end. The last question, we have a mixture of 2 gases, and we can get the moles of each. So since I know the mole ratio, I can do some quick little math. So I have 10 moles total. For every 1 mole total, I have 0.67 moles of hydrogen, and so that's where the first part comes from, where I am literally canceling out units for mole total here, and I got my moles of H2, and so I got my moles of H2 here calculated. And so since I know my mole total, I can subtract my hydrogen in order to get oxygen. Now, I did do sig figs just based off what's given in the problem. I got 10 moles total. There is no decimal, so it is only one sig fig, so I rounded that to be 3 moles of O2. Alrighty, we have one more practice problem. So, here we go. We have partial pressure. This one, as I stated here, is a bit more complicated, and most likely College Board would ask it. However, the chance is not zero. So we're going to go ahead and do one practice problem like this. So go ahead and read this to yourself, read some hints here, and then try it out before I talk about it. All right, ready? Here we go. So we're using the relationship here in order to do some stuff. And so on the bottom here, I have my total pressure by getting my fluorine and getting my hydrogen to get the total atmospheres. Then I'm using the relationship here where I can move stuff around in order to get total moles and moles of A and all that stuff here. And so then I can do the mole ratio of that, which is just the 0.5 divided by the 2.5 atmospheres, because these were atmospheres, and I got that, and that relates to the number of moles, 0.2 moles of hydrogen to 1 mole total. Now, if you're like, what the heck, I don't get it. Like I said, this is a way more complicated problem, and College Board probably wouldn't ask one like this, but again, you take the relationships that are given up here, and then instead of having X, you put this over here, and then I just manipulated it to have the moles on one side, the pressure on one side, and then I got my mole to mole ratio by dividing the pressure of hydrogen to the pressure of total. And so I just took that math, and it ended up equaling 0.2, and then 0.2 divided by 1 equals 0.2, so that I can just get that ratio of 0.2 moles of hydrogen to 1 mole. So again, if you're like, whoa, again, the math isn't like too hard, but most likely College Board wouldn't ask a question like this. Overall, ideal gas laws are not too shabby. You got PervNERT, you plug and chug, you got combined gas law, and then you got the partial pressures, which might be slightly harder. But otherwise, this section is relatively easy. It's good old algebra and doing the guess method to organize your thoughts. All right, that's it for this section. Bye!